Okay, so welcome everybody. Today we're going to be talking about WebAssembly components. This is not the first components talk of the day, and hopefully this will give you kind of a more lower level, kind of intimate understanding of what components are. But before we begin, real quick, a little bit about who I am. I'm Ryan Levick. I'm an engineer at Fermyon. The best place to find me is on the Bytecode Alliance Zulip. I have kind of completely abandoned the social web, so find me there. Why are we here, though? What do we want to actually talk about? Well, my main goal for today is to give you a little bit of confidence. To come away from this talk feeling like you're not completely lost. If you've seen some of our other talks about components, depending on how deep they've gone, you may have felt, okay, am I in over my head a little bit? So we're going to dive pretty deep and much lower level than you probably practically ever will have to go. But my hope with that is that when things are going right, you're feeling confident, and when things go wrong, you're not feeling too unconfident because you've seen some of this before. So in general, how this relates to sort of other talks that we've had at the conference so far, we had Torsten's talk on the component model yesterday from a very high level as a user of components. That's really wonderful, and hopefully most of your usage of components will be at that level. You'll just be able to use components, they will work the way that you expect them to work, and everything will be fine. And then we had Luke earlier today talking a little bit about a subslice of components, the future of components, particularly around async, very low level, talking about ABIs and how memory is used. We'll be touching on a little bit of that today as well, but my hope is to kind of sit between the two of those and help bridge the gap between those two worlds. So the central question for today is, what are components? That's really what we're going to get at. And we've already had this question at the conference quite a bit. Hopefully you have an idea of what components are as kind of a reusable and pluggable system for sharing WebAssembly code and building larger pieces of software out of smaller units. But the talk today is more like, what are components really kind of on disk in the binary? So the first thing that we're going to answer with this is that components are an extension of core WebAssembly. And this kind of begs the question then, okay, what is core WebAssembly? Maybe you've never heard the term core WebAssembly, you just know what WebAssembly is. And the answer to that is that core WebAssembly is what WebAssembly has been since its inception. So if you've not dealt with components before, then just substitute core WebAssembly with WebAssembly, because that's what it's been. And this is really meant as a way to differentiate between the core WebAssembly modules, plain old Wasm that we've been using since the inception of WebAssembly, and WebAssembly components, which is sort of an extension on core WebAssembly modules. So now I'm going to attempt, against my better judgment, to actually do some live coding or building of core components and core modules. So I'm going to pop over here, and then let's clear the screen here and go into module here. I'm just going to open this up in VS Code because that's probably a bit easier, and hopefully this is fine to see. So here's some Rust code. I'll be using Rust today, but if you don't like Rust, that's fine. Hopefully it shouldn't be too much of a distraction. This can happen in any language that can compile to WebAssembly. And we have a Rust function here. It's very simple. It's called add. It takes A and B as uSizes, which are pointer-sized integers, and it returns that uSize integer as well. So this is basically as simple as it gets. And if you're not familiar with Rust, then this extern C here is basically saying, treat this as a C function instead of a Rust function. And no mangle here just means, really, I want to call this thing add. So when I compile it, don't kind of change its name, don't change any symbols and things like that. And really, the only difference between this and a regular kind of straight out of the box hello world is we're doing a different crate type here. So if you've done Rust before, this probably looks very familiar, and if you've not done Rust before, then it probably doesn't look too scary to you. And we can go ahead and build this, by doing Wasm 32 unknown here. And we can build it, and I'll go ahead and bring it over to this folder here so that it's a bit easier to work with. So now we have WebAssembly, and this is a core WebAssembly module. This is nothing. There's nothing special. We've been doing this for a very, very long time now. So we're all on the same page. Hopefully, we've got core WebAssembly. Let's come back here real quick. So now is where we start to dive deep in. We're going to inspect our core module a little bit and kind of poke and prod at the binary. In order to do this, we're going to be using a bytecode alliance tool called Wasm Tools, and this is a whole suite of tools for inspecting WebAssembly modules as well as components. So let's head back over here. And I've got Wasm Tools already installed. And if we take a look at, you can read through what this does. There's a whole bunch of things here, like validating that your module is a valid module. But the one that we're going to be dealing with today is print here. So I'm going to do Wasm Tools, print. And then I'm going to use this skeleton option here. And what the skeleton option does is gets rid of all of the actual code from our WebAssembly module when we print it out, and instead just look at sort of all of the scaffolding, the skeleton of the WebAssembly module, so that we can kind of look at the stuff, because we don't want to actually read just raw WebAssembly code. That's not super interesting for our purposes right now. And we'll take a look at what that looks like. Oops, I got to spell it correctly. Wasm Tools is not a tool, apparently. So here we go. We have a module. And if you've never looked at WAT before with the WebAssembly text representation, then this might look a little bit confusing to you. I'll talk about it in just a second, but hopefully it's not too overwhelming. There's not a ton here. At the very end, down here, you can see kind of the kind of core of what's going on. And really what we have is we're exporting some memory, and we're exporting our function here, add. And if we look at what add actually is, by going up here, we can see that it is a function, and it looks how we would expect it to look. It takes an I32 and an I32, that's A and B, and returns an I32. That's our result. So pretty straightforward. Okay, nothing too big there. I want to give a shout out also to a Wasm analyzer as well, as a way you can drop in a WebAssembly component and get a more kind of visual representation of what we just saw. So if you don't want to be in your terminal and rather just poke around in a browser, then this is a great tool for doing that as well. All right. Here's a QR code if you want to quickly snap a picture of that you can go ahead and access it. Also giving a shout out to Mozilla for creating these WebAssembly text format documents as well, to be able to understand how the text format actually works. If this is all very intriguing to you, like, oh, I want to understand how to read raw WebAssembly, then this is a great resource for doing that, where you can learn exactly how core WebAssembly at least works at the kind of low-level text representation. By the way, I should mention the text representation and the binary representation are more or less one-to-one, so when you're reading the text format, you are essentially reading binary code then just in a human-readable way. So now we're going to start getting away from core modules and start messing with them in ways that they're not supposed to be messed with. All right? Let's pop on over here, open this back up, and you might be thinking, okay, add is great, but that's I've never written an add function before. What about some like real code? What if we want to take things like strings or something like that? So I'll change this here to uppercase, and A will then become string, and we're gonna return, and gonna return a string, and all we're gonna call here is to uppercase on A. So now instead of adding two numbers together, we're going to take a string and return an uppercase string here. And Rust is already giving us some warnings here saying string is not FFI safe. That's because passing strings from WebAssembly to the outside world, or passing Rust strings from WebAssembly to the outside world is not safe to do, because the in-memory representation of Rust strings is not really stable. It can change from compiler version to compiler version. You're not supposed to rely on it. And when we're passing from WebAssembly to the outside world, we need to know exactly how that string is meant to look, because the outside world needs to know that to be able to read it, to be able to interact with it. So Besides that, though, if we go ahead and compile it, besides getting the warnings, everything is working fine. And I can go ahead and copy it over again. And let's take a look at what this looks like. And we kind of have the same thing as before. We're exporting an uppercase function now, so a different name, but it's the same. And if we look at what uppercase, if we look at what uppercase looks like here, this is where it starts getting a little bit strange. It's like, okay, I'm taking 4 params here, I'm not returning anything. What's that about? It doesn't necessarily make sense. The reason for this is because the compiler is trying to do its best to do what it would expect to do with the Rust representation of strings that it knows about. But of course, we as WebAssembly users and components, when we want to use them, will want to think about these types at a higher level than just I32s. So can we do better than this? And spoiler alert, yes, we can. So the real problem at the end of the day is that core module functions only take and return integers and floats. They don't have any understanding of higher level types like strings or lists, vectors, or structs or enums or anything like that. It's really just integers and floats at the end of the day. And the problem that we want to get at is, how do we actually represent complex types in memory? How can we make sure that we talk in terms of these complex types? And WebAssembly's been around for a while now, and of course, not everybody is just writing add functions. We actually are capable of handling this situation, but how do we do this? Well, the answer is through sort of what I've termed ad hoc and shared everything ABIs. Okay, that's some mumbo jumbo. What does that mean? Well, let's start with ABIs. This is probably something you've heard before. An ABI is an application binary interface. So this is really at the lowest level when you want to call a function. How do you pass arguments and how do you get return values? Where do they end up? And if you're talking about a regular instruction set, this would really be like, which registers do things go into, when do things go on the stack, blah, 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 blah. So this is really what we want to be focusing on, is this low-level detail. This is all ad hoc, meaning that for every user of a module, the author of the module and the user of the module who wants to call into the module have to kind of ad hoc come up with an agreement about how these things will be done. If you want to pass a string around, you as the module and you as the user of the module need to be on the same page about exactly how that will be done, down to where things will be laid out in memory, how to read them, how to find things, what are the order of arguments, so on and so forth. And shared everything here refers to that the whole world is open to both sides of this equation. The module author and the module user both have full access to the memory that is being used by the module, and so if they have to be on the same page, and if they mess it up, there are kind of large consequences there because they both have the same view of everything. And if you're feeling like, oh, shared everything, that seems like it's kind of in contrast to shared nothing that I heard Luke talking about earlier. That's exactly what we're kind of getting at. So keep that in mind. So what does this look like? Well, just imagine 2 modules wanting to try and talk to each other. And module A wants to call a greet function that kind of at a high level just passes a string. And presumably that string then gets printed out. Well, module A thinks about that string. Maybe it's a Rust string because it's written in Rust, or it's a JavaScript string, or whatever module A happens to be written in. But when we want to call module B's, when we want to call that function, the greet function, we can't pass that representation because module B doesn't understand that, or in the case of Rust, it might not even be a good idea to do because it can change from compiler version to compiler version. And so really, the greet function needs to end up translated into a kind of lower level core module representation where we can just pass, again, either integers or floats. And so a nice way to do this probably would be the pointer to your data and the length of your string data, and to pass that instead. So module A can kind of lower down from that string representation into this lower level representation of pointer and length. And that's fine. Core WebAssembly understands 2 I32s, no problem. And what module A will do is then allocate the string data into shared memory that module B and maybe other things have access to, and it will point towards that shared memory there. And then it can pass it over. And module B points at the same shared memory, and it knows, okay, I'm on the same page. I know that I'm going to go ahead and kind of collapse that down into a string, and I know exactly how that string is laid out, and that's all fine. So this is how it kind of works today. Everybody is on the same page, but these two modules have to be really on the same page here. And if you want an example of how this has been done in the past, you have tools like Wasm-bindgen, which is a Rust tool for doing this, where WebAssembly written in Rust and the JavaScript running in the browser can interact with one another, and basically Wasm-bindgen generates a whole bunch of code to kind of set both sides up to work in ways that both sides expect and understand. So what are some limitations here? Well, the ABI here is all a convention. This is not specified anywhere. This is just both sides kind of coming to an agreement. And if there is a module that doesn't conform to this, it just simply won't work. Conventions are easier to mess up than standards are, because standards are a way for us all to get on the exact same page, whereas conventions are like, well, if you want to, it'll work. If you don't, it's no big deal. Memory is shared here. It can be corrupted in certain ways if things go wrong. Both sides have to kind of trust each other and be on the same page about each other and hope that they don't really step on it. So the point here isn't that this can't work. It's that it can work, but it's kind of brittle. And the ABI can change depending on language as well. And really, like, if you were intrigued by what Luke said earlier on his talk about async, like, none of that can work if we're kind of sharing everything and we don't have a way of kind of specifying these things at a low level and getting on the same page. So components we can think about are the opposite of this. Components are a canonical ABI, an ABI that everybody is on the same page about. It's specified. And it's built on top of a shared nothing architecture, where both sides don't share the same memory. They have their own memory and then have ways of basically saying, if you want to read from something, here's how you do it. And I'm not going to go into details about the canonical ABI, because that's basically several talks in and of itself. But if you want to read about it in great low-level detail, then there's the canonical ABI explainer as well, which you can find here. OK, so enough theory. Let's create a component. And the first thing that we're going to need to do, here, let me close this, and open up first component. And because my typing is not going super well, I'm just going to read through code as opposed to typing it. So we're going to create a component here, and the component is doing the same thing as before. It's just using a bit of tooling in order to do it, and it's going to take a string as input and output another string. And the way that we start doing this is by specifying wit, which is our interface description language for specifying what our component will look like. And here we just have one simple function called toUpper that takes string as an input and returns a string. And of course, our code here as well is all very high level, taking strings and returning strings, and we don't have to worry about this low-level ABI detail, because that's all taken care of the tooling. And the tooling knows how to do that because this is all kind of pre-specified ahead of time. And so the way that we're going to do this is just like before. We're going to build a core module. Oh, sorry, I got to go to first component here. So we're going to build a core module here, and now we've ended up with a core module just like before. So we don't have a component yet. We have to take our core module and turn it into a component. And the reason for this is simply that most compilers nowadays don't understand components yet. And that will change as time goes on. But for now, compilers understand core modules and don't understand components. But because components are simply just a wrapper around core modules, that's really not a big deal. We can go ahead and copy over our core module here real quick into this folder. And then we can run Wasm Tools component new here. Let me make this a bit bigger. Passing in our core module and then wrap it up and make it into a component itself. So if we go ahead and run that, we now have component.wasm here, and that's an actual component. So if we go ahead and inspect it, we'll see something a bit different than we saw before. Let's skeleton component.wasm and pass it to less. So this looks similar to what we saw before, but you'll notice a few key differences. We're talking about a component here. We now have core module instead of module before. And if we scroll all the way down here, then you can see we're exporting to upper, which if we look at to upper real quick, we can see, we can see the various pointing to the core module function that will be exported and actually implement this on behalf of us. So we're good to go here. And here is kind of the key to how things actually work. So this is where we have specification of that the canonical ABI for how to lower string data into this lower level representation that core modules understand of presumably a pointer and a length, and it includes ways to kind of change that that translation, including how the string is encoded here. So the thing to take away from this is kind of the mechanism that Luke was talking about earlier, where instead of talking about string encodings, he was talking about a way to asyncify this lowering and lifting of components, of functions inside of components to their module representations here. All right. So a quick kind of overview of this canonical ABI. We have no shared memory as opposed to previously where we were sharing memory. We have flexible conversions through core WebAssembly definitions, so we don't have to kind of hard code exactly how things are converted. We're able to customize that in certain ways. And we're able to do that when we're lowering from higher level types into linear memory, so going from strings into how they're represented as bytes in linear memory, as well as lifting from linear memory into higher level types. So going from that linear memory to what your language of choice, whatever it may be, understands as a string. And there are options for customizing how this happens through these things called canon ops, which allow you to do things like, in the case of strings, specify how the strings are laid out in memory through their encoding. So we're dealing with UTF-8 in this case. Real quick, a tool that I wrote, if you just want to kind of look into a component and understand what it kind of looks like, is called WEPL, which is the WebAssembly REPL here. And if we do, I have to go to the right folder, first component. We can open up our component here. And we can see the exports that we have, and the imports which we have none here, and understand how our component runs. And in fact, hopefully this works. I've been messing with the parser, and I hope it didn't screw things up. We'll see. We can actually go ahead and call our function as well. So if you want a way to kind of mess around with and poke at your component from a high level, this is a tool that allows you to do that. All right. So I think we might have a bit of time to talk about how we actually run these components. I'll quickly go through that as well. So how do we actually run them besides using something like WEPL, which is an already kind of built runtime for running components? Well, let's look at how a host is built here. And again, sorry if you're not used to or don't like to read Rust code, but I'll try and make this as simple as possible. So we're simply reading our component from disk here, and we kind of set up our Wasmtime, which is the runtime that I'm using in this case, engine here. We set an engine, which is what actually runs WebAssembly. We set up a store, which stores data. We set up a linker, which allows us to take in outside implementations for imports. We create a component here. We instantiate that component through the linker as well, and then we're able to get the function, the toUpper function here, and then call it using these parameters with hello here, and presumably we should get back hello all uppercased, and hopefully that works. And we did. So that's good. So yeah, that's this code is very, very simple, but yet it's still fairly low level when you interact with components on your own. You probably won't be interacting with them in exactly this way because we have this specified tooling and we have things like wit that specify exactly what our interfaces look like. We can build higher level and more higher level tooling on top of that and be able to run components without you having to actually do the low level instantiation of a runtime, a linker, and all that stuff. All right. So I'd like to sort of shift a little bit for the last thing, which is where does Wazi fit into this? So we've talked about the component model a whole bunch, and we know that we have Wazi, and especially a new version, Preview 2 or 0.2. What is the difference? Like, where does the component model end and Wazi begin, if you don't quite understand that? Well, Wazi, Preview 2, and beyond is built on top of the component model. And essentially, the takeaway from this is that really, Wazi isn't special in that regard. Wazi is simply just a usage of the component model. So if you want to build your own competing standard, which please don't do it because that would be very annoying, but if you wanted to, you certainly could, because Wazi at the end of the day is simply just a usage of the component model where the wit definitions are all kind of agreed upon as being the right way for doing common things. So they're just useful set of wit worlds for doing common useful things like reading from disk or talking to the network or something like that. And that's all that Wazi is just what we've seen here today, where everybody says, yeah, that wit file looks fine, we'll call it Wazi. That's it. All right, so what have we learned, or what have we gotten hopefully a little bit more comfortable with, is that components extend WebAssembly modules. They provide a way to interact with WebAssembly code in sort of a standardized way where everybody is on the same page, and you don't have to know exactly how WebAssembly was compiled or how it expects things to be laid out in memory. It all just works. It's done in a shared nothing way, and it uses these higher level complex types that you would expect to be able to use, like strings and lists and structs. And we have a growing set of tools for poking at these components, which we've seen some of them today, like Wasm Tools and WEPL. And really, at the end, Wazi is nothing but a standard set of component interfaces. So again, if you want to create something that looks like Wazi, you can, because really, at the end of the day, you just need to create a set of components. And that's it. Thank you very much.
I can ask you a question, Ryan. So one thing that I've never understood about this whole component model thing with the shared nothing memory is, in your example, when we are passing a string between components and there is no shared memory, how is that not, or is it impacting performance like?
Is it impacting performance? So there are certain optimizations, kind of. The simple answer is yes. It does impact your performance above what you would be able to accomplish if you had shared memory and you were able to pass pointers around. Because there is a case where you might have to copy data. The nice thing is that the idea of lowering, going from your complex string, lowering to an ABI, and then raising back up into some other language's representation of string is sort of the most naive case. And in that case, yes, memory will be copied and has to be copied. But there are certain optimizations, because we're dealing with these kind of high-level types and a high-level understanding of how components interact with each other, where copying might not be necessary. And in fact, there are some kind of compile time transformations that can happen that may be able to eliminate copies. In the case where you're sure that you need to avoid copying because you have large amounts of data and you know you're going from UTF-8 encoding to UTF-16 encoding, and that's a performance issue, there are ways around that by using resources. So yes, naively, there is a performance penalty here, but sort of practically, for most use cases of things, that performance penalty is negligible and oftentimes can be completely elided. So. All right. I guess that's it. Thank you very much.